Survey and calibration is the process of recording measured data and using it to create a reliable virtual model. How do we model your facility? We begin with a perimeter check. Following along the walls of the facility, we inspect the dimensions of the walls and adjust the model accordingly. Existing CAD drawings are used as a start point and then are refined on-site. Air leakage around the perimeter is mapped, accounting for semi-sealed piping cutouts or holes in the raised floor. Next, we survey the cabinet and grill layout, accounting for details such as placement and type. Details of grills or cabinets may be recorded for the model if the objects do not already exist in our library. The objects will be simplified later using a flow simulation to make sure all important characteristics are captured. The remaining objects on the floor, such as PDUs, cracks, and architecture, are then mapped out in the model. Dimensions, make, and model will be recorded, and library items placed if they exist. If you have opted for our top-level Platinum service, our engineers then visually inspect the IT equipment, adding or modifying IT assets in the model to match. This includes make, model, U-slot position, orientation, blanking, power connections, and any other objects found in the cabinets. This level of detail allows us to predict the inlet temperatures of each piece of IT. All major airflow blockages above and below the underfloor will also be accounted for in the model. These obstructions include chilled water piping, power conduits, network cables, beams, columns, PDU or cracked substructures, and other miscellaneous items. If there is a false ceiling incorporated in the cooling design, we will also include all relevant obstructions in the planum above. Finally, any ductwork or containment architecture is assessed and added into the model. With the physical architecture mapped out, our engineers can then move on to airflow and temperature measurements. Flow rate is measured for every accessible grill, using proprietary methods, one of which uses a flow hood in conjunction with a vane anemometer. We are able to accurately record grill flows for any raised floor. Using a flow measurement matrix, air velocity is measured across the return of a crack. The velocity measurements from all cracks are compared to establish relative flow rates, which are later scaled to match room load. Temperature sensors are placed on the supply and return of each crack. These are placed to capture variation in air temperature returning to each unit. Temperature and airflow measurements can reveal the true operational conditions of each crack unit. Where necessary, a thermal camera or temperature sensors are used to record the rack inlet temperature over the area of the inlet vents. Finally, the model is solved and all measurements are compared with the simulation. Our engineers then continue to refine the model through additional iterations in a process called calibration, which uses the measured data to check that a model is representative of the real facility. Where discrepancies are not obvious, we investigate further, often uncovering deviations from design or unknown operational issues. When the process is completed, we can use the model to recreate power and cooling system operation and highlight areas in the live facility that need improvements or changes.